Good morning. I think it's morning in Europe still, right? I'm not never quite sure. But
Yes.
good morning, good afternoon, wherever you are. So I'm here to present my paper, which is, as Nuno said, mining feature relationships in data. This is a short talk, so it's only 10 minutes. So the motivation behind this paper comes mostly from the area of machine learning of association rule mining, which is this whole idea of trying to find relationships between features or attributes in a data set. So the classic example that a lot of people have talked about and may or may not be entirely true is diapers and beer. So the story goes that sometime in the 90s, I think, a supermarket employee noticed that a lot of people would be buying diapers and beer at the same time. And so the logic was, then why don't we put the diapers next to the beer in the supermarket? Again, I'm not sure quite how true this is, but it's kind of a origin story for association rule mining. So in this case, the rule that we've found is that diapers and beer occur together, and so maybe when you buy diapers, you'll also buy beer. But I kind of have an issue with this as a machine learning person, which is that it doesn't capture symbolic relationships very well. So a lot of relationships in our data sets, if we are thinking about just the features or the attributes, often tend to be symbolic in nature. So the classic example is if you go to the doctor and they measure your BMI, then that's your weight divided by your height squared. When you think about buying a house, then there's a variety of different factors that you would take into account. For example, how many bedrooms there is, how many bathrooms, how much land is on the property, and so on. And there has been some work done in association rule mining to deal with this continuous data or these symbolic relationships, but it tends to not be very interpretable when you have to use things like binning or one-shot encoding or so on. So the big idea of this paper is, can we use GP for this? We know that tree-based GP is suited to representing symbolic relationships. There's been a lot of success in symbolic regression and finding good trees to model symbolic relationships from some inputs to an output. And so my question in this paper is, can we use GP to represent these feature relationships as GP trees? So these 4 trees you see here, which is from another paper, but is a good example of it, would show, for example, 4 different trees that would represent different relationships in the data. So doing a variety of things, taking maximums, additions, subtractions, if statements, all of those things that we're used to doing in GP. And so this paper was all about trying to explore this idea of finding what I call feature relationships in data, which is a symbolic relationship between some set of features and an output or a target feature. So if we go back to our example of BMI, we could represent this as a tree in this form, where we multiply the height and then use the height as the denominator and the weight as the numerator in our fraction, and that would output our BMI. So if we had these 3 features in our data set, we could then find, through using a tree like this, we could find this relationship that's sort of inherent to our data. Obviously, this is a bit of a contrived example, but it's hoped that in real data, we would also be able to find these sort of underlying relationships. One of the key things in this work is that the output of the tree should correspond to a feature in our data set, and that we want our inputs to our trees to be different features, right? We're trying to find relationships between features and other features. It's unsupervised learning. So another important component of this work is that we want to find a set of these relationships. We don't just want to find one of them. We would like to find a set of diverse relationships that give us different insights into our data. In this work, we use a form of speciation to do this. So we look at the output of each tree and then see which feature that output is most similar to. So for example, in here, we had an output which is very similar to BMI. And so BMI would be what we call our target feature for this tree. And then we essentially cluster our trees across their whole population based on their target feature. And so, for example, you may get 4 different trees here that would all be trying to represent the same target feature, so maybe BMI, and then another set of trees here which is trying to represent something else, maybe your height or your blood pressure or something else in the medical data set. And the benefit of doing this is that it means we can then restrict crossover to be within the same species. So we want, these 2 trees to be doing crossover and exchange information, not ones that have different targets. We also place a limit on a number of species, so we get a reasonable amount of diversity, but we're not just making these really spurious relationships as well. So how do we actually measure the relationships between the features? So our tree will produce some output, and we want to know what's the most similar feature to this given output. In this work, we use absolute Pearson's correlation for a few reasons. Firstly, a scale invariance. So if we find a linear relationship, for example, we don't care if it's a 10 times a linear relationship or 100 times. We just care about the actual shape of the relationship itself. So we want a measure that's scale invariant, and absolute Pearson's correlation gives us that. We also want something that's invariant to directionality. So a negative and a positive relationship are kind of telling us the same thing. It's just which way round you've got it. And so again, by using the absolute value, we means we're not discovering the same relationship twice in different directions. And finally, it's also bounded between 0 and 1 in the way that we formulate it, which makes it really easy to analyze. You can get an intuitive idea based on where it falls in that range as to how good of a feature relationship you've found. And then a final important component to this work, well, in a 10-minute talk at least, is that we use parsimony pressure because we want relationships that we can understand, right? There's no point making a really big complex GP tree that tells us really well how these 100 features correspond to this one output feature, because we can't really understand that. And so we use a really simple form of parsimony pressure, which is just adding a small penalty to our fitness based on tree size. In the paper, we did a bunch of experiments with 8 data sets and different amounts of parsimony pressure. But again, because it's a short talk, we just look at some examples of the rules or the relationships that we found in this talk. So the wine data set, I'm sure you are all somewhat familiar with it. You've got 13 features, and the data set is used to categorize different types of wine. Obviously, it's a fairly simple data set, but it's a nice toy data set to show you how this might work. So this is our evolved tree here, and this is actually corresponding to this feature relationship here. So flavonoids is our target feature, and we're saying that's equivalent to taking the minimum of the total phenols times the hue and the proanthocyanins. So we've found that the closest output here is our flavonoids, and so we're saying this is the relationship we've discovered. We've got a cost of 0.098, which is a lower cost. The cost of 0 is optimal, so it's a pretty strong relationship. And then if we actually look at the features being used, we can see that our target feature, our flavonoids, is to do with the color of wine. And then all of our 3 other input features here all also correspond to aspects of color. So phenols, hue, obviously color, and then the proanthocyanins are a type of compound that only occur in red wine, and we can see that we're using that as part of our decision as to whether or not, or how strong the relationship is with flavonoids. And so we're looking at something like this, and in theory, this is obviously a very initial piece of work, but in theory, a wine expert or someone in a winery or a vineyard could perhaps better understand what is affecting the color of wine. Of course, run it on a bunch of different data sets, so you can see you get a variety of reasonably small trees, often with only a few input features. So this one here has got 2 different input features and gets a perfect cost. So we found an exact relationship here. Whereas even on the dermatology, the skin cancer data set, we can get quite concise relationships with quite good accuracy. So in conclusion, this work introduced a way to automatically discover these non-trivial and diverse symbolic feature relationships in data. So in an unsupervised sense, just looking at the data itself. The trees were small enough to be interpretable, but still gave us strong relationships. And as I alluded to, this is a very initial piece of work, so there's lots of future work and there's other work to build on as well. So how do we measure interpretability is a age-old question, of course, but in this scenario especially, this smarter way to doing speciation that was just a very brute force way. And then also looking at things like multi-objective optimization, so interpretability and cost being two different objectives. But yeah, thank you, and I will finish here and have time for a couple of questions.
Thank you very much. Thank you for your talk. We already have a question from Leonardo Vaneschi. Leonardo, can you read your question? Thank you.
Thank you, Eric. Can you hear me?
Yeah.
Okay,
Yes,
so the
yes.
question was, Andrew, hi, thank you very much for the nice presentation. So the question basically was, if I understand correctly, you have evolved one global population and you have partitioned it into demes. And there is each deme is specialized for one particular feature, right? But what is the advantage of doing this compared to considering one particular feature and running one independent GP for that feature? You see what I mean? So having complete independent populations for each feature instead of having one global population.
Yeah, that's a good question. I think primarily it's from a sort of efficiency standpoint. So if you think of a data set with 1,000 features, you know, like we get more and more these days, if you try to run it 1,000 times, and we all know that GP is reasonably slow in compared to other methods, then trying to do it 1,000 times is going to take a lot longer. Whereas if we can make a method that can find the 10 best relationships in one run, then it's a lot more usable in practice.
So Andrew, sorry, the number of demes is not prefixed.
Yes,
it is decided
yes, so
during the. I didn't catch this. Okay.
Yeah, it's a hyperparameter.
Very good. Thank you very much.
Okay, thank you both, Leonardo and Andrew. There is another question from Bill.
Yeah, I was just thinking that if you want people to take up your work, then on the slides it's much better to use real names rather than the symbols. I mean, you had one example where you had to explain what the slide meant by putting text next to it. And there's no reason why you couldn't put that text into the tree itself. So that generally, if you want people to understand, then use terms that they're already familiar with rather than inventing your own.
Yeah, that's a very good point. It was an oversight on my part, but thanks for that, Bill.
Okay. Please, Bill, sorry, I interrupted you. You were still commenting.
Of GP and the speed of GP, I think there are very fast GP interpreters out there now. And the assumption that we're slow compared to other techniques, well, it depends on what other technique you're looking at. I mean, GP is, I would guess, would be faster than some deep learning approaches.
Yeah, that's certainly true as well. But I suppose what I was more trying to get at is there's a trade-off between running your run of GP for much longer versus running a bunch, say 1,000 different runs for a short amount of time. It's probably better if we can do speciation and get a smaller set of results in a single run, and then therefore run it for more generations. But yes, speed is very much relative.